So today, let's take a look at the schematic of this interesting power supply from the previous video. And of course, let's explain how does this work. It's a 5 volt 10 amp power supply, a switching one. I was fixing and testing in the previous video, and now let's dive into the schematic. As you can see, it's a switching power supply, and this topology is a flyback, which means that it has one switching transistor and a transformer with a ferrite core with an air gap. And in a flyback, when the transistor is on, the diode on the secondary side is in reverse and not conducting, and when the transistor turns off, the diode starts conducting and passing a current from the secondary into this capacitor bank. And so a flyback switching power supply, unlike a forward or half bridge or bridge power supply, does not pass the power through the transformer directly. It basically accumulates the energy in the core of the transformer in one step, and then, in the second step, the energy goes to the secondary side. When the transistor is on, this side of the secondary is negative and this diode is not conducting, and when the transistor turns off, the polarity changes on the windings, and now this side of the secondary is positive and the current goes from it into the capacitors. And this one is kind of a more old school traditional flyback with no control chip and with no MOSFET. It has just a bipolar switching transistor and an auxiliary transistor. Here's the main transistor and the auxiliary transistor in the schematic. And there is no control chip, so it's a self-oscillating flyback. And now let's dive into the schematic. Let's go through it from the input all the way to the output. And it's more or less a normal flyback switching power supply as you would expect, but there are also some oddities in it. So the mains comes in, there is a fuse, an NTC thermistor for inrush current limitation, a metal oxide varistor for overvoltage protection, this X2 interference capacitor, a common mode inductor, basically a common mode interference filter, another X2 capacitor, then some class Y1 capacitors going to ground to basically suppress a differential mode interference between live or neutral and ground. And there is another class Y1 capacitor going to the negative of the primary smoothing electrolytic capacitors to reduce the high frequency ripple on the primary DC side, basically. And there is also an interference capacitor going from ground to the negative of the output, and this one doesn't have to be a safety class capacitor because it goes from the output to ground, not neutral or live. And here's the bridge rectifier, which I drawn as individual diodes to be more clear. And there is also a voltage switch, which switches between the operation for the higher voltage mains, 200 to 240 volts, or the lower voltage mains, which is used in some countries, from 100 to 120 volts, or simply marked 110 volts on the board. And this switch basically, when you turn it on, changes it from a bridge rectifier to a voltage doubler. When the switch is off, it's a normal bridge rectifier which basically charges those capacitors both in series. But when the switch is on, for the lower voltages of mains, it turns it into a doubler. In one half cycle, basically, it charges the upper capacitor through this diode, like this, and in the other half cycle, it basically charges the lower capacitor, like this, through this diode. And so it basically uses those two diodes as a voltage doubler, and the other two diodes are basically just anti-parallel to those capacitors, and they kind of protect them against negative voltage if something goes wrong. Even though, of course, this shouldn't happen in a normal operation. And here you can see a discharging resistor for this capacitor, and those discharging resistors for this capacitor actually double up as a starting resistor, which injects a small current into the base of the main transistor to start it up. So the discharging resistors basically double as starting resistors and also as balancing resistors to balance the voltage between those capacitors, especially when it's using the higher voltage mains. And it's a bit weird because the upper resistor is just one and the lower ones are two in a series, but of course, in total, they have the same resistance as this one. And here is the main switching transistor, which is bipolar NPN, not the MOSFET. It's a bit old school, but it works nicely, and it switches the rectified mains voltage into the primary of the switching transformer, and it has some snapper network here with this diode, capacitor and resistors. It basically limits the voltage overshoots on the primary when the transistor turns off. The overshoots are rectified by this diode, and it goes into this capacitor and it's dissipated in those power resistors. And there is another snapper network on the transistor here, a series resistor and capacitor, and it probably is there to limit the dVdt, the rate of voltage rise on the transistor when it turns off. And of course the transistor has a current sensing resistor in its emitter, a very low resistance resistor, and it senses the current. And if the current is too high, also the voltage drop on the resistor is too high, and then at about half a volt, it's enough to turn this transistor on, and this one pulls the base of this one down, and so this one turns off in case of an overcurrent. It's more or less a typical setup with the main transistor and the small transistor sensing the current and turning it off like this. So this all is quite common so far, but now the oddity. This circuitry here is kind of crazy. But now let's take a look at the secondary side. Here is the secondary, which is rectified by this double diode, which is in parallel, so it works as just one big diode. And it rectifies the voltage and it goes into this capacitor bank. There is the loading resistor, so it never runs with no load. Here is the interference inductor to reduce the high frequency ripple at the output, and another capacitor for better ripple filtering, and also some anti-parallel diode. I'm not really sure if this is necessary, but anyway, it's there, and it goes into the output. And here is the voltage feedback circuitry with the voltage reference TL431, which basically starts passing a current from here to here when it has about 2.5 volts at the input. And there is a voltage divider with those resistors and a potentiometer for voltage sensing, and when the output voltage reaches the desired level, then the divider basically gives 2.5 volts, and this reference starts passing a current through this LED. It's an infrared LED inside of an optocoupler, and this is one half of the optocoupler, and the other half of it is this. It's actually split in the schematic, but in reality it's just one component. The other side of the optocoupler has a phototransistor, and when it's illuminated by this infrared LED in it, it starts passing a current. So when the output voltage reaches what it should be, this transistor turns on and passes a current to limit the duty cycle, so the voltage no longer goes up at the output. And there is an auxiliary power supply for the optocoupler with those diodes rectifying the auxiliary winding, and through this resistor it charges this capacitor. The optocoupler basically takes the voltage from this capacitor and passes the current into the base of this transistor, and this one basically helps to turn this transistor off a bit earlier in each cycle to limit the duty cycle. And this voltage sensing circuitry also has some resistor and capacitor as a negative feedback for stability. It basically slows down the changes, so it doesn't overcompensate sudden changes at the output, especially when you suddenly increase or reduce the load. And also to prevent oscillation of the feedback, basically. It's the condition when the feedback overcompensates, undercompensates, overcompensates, undercompensates. It's necessary for the feedback not to react too fast. And here's an indication LED with a resistor, and here's the potentiometer to adjust the output voltage. And the output voltage is 5 volts and the reference voltage is 2.5 volts. So the resistors in the divider should be equal. This one is 2 kilo ohms and this one is 1.5 kilo ohms. So you have to set the potentiometer to about 0.5 kilo ohms to get 5 volts. So it all makes sense so far, but here's the weird part. Of course, the power supply has to oscillate. It's a self-oscillating flyback, so it basically has to oscillate because there is a positive feedback from the auxiliary winding back into the base of the main transistor. And the feedback probably goes through this side of the auxiliary and through those components back into the base. It's usually just a resistor and capacitor, but in this case there is a diode added, which is strange. Normally it's just a resistor and here a capacitor, and normally it tends to have a lower capacitance. And the capacitor is often used for the timing. It basically limits the maximum length of the pulse, because during the pulse this capacitor charges to negative on this side, and then it can supply no more current into the base and the transistor has to turn off. But in this case the capacitor is bypassed by this diode, so it never charges to negative here, and it basically supplies a current into the base forever when there is a positive voltage on this side of the winding. So the timing is done a different way. Here it's done probably by this current sensing resistor. When the transistor is on, the magnetic field builds up in the core of the transformer, and so the current of the primary goes up. Because basically the more magnetized the core is, the more current goes through the winding. So the current goes up, and so also the voltage drop on this resistor goes up until it reaches about half a volt. And then this transistor turns on and pulls the base of this one down, and this one turns off. So the maximum pulse length is limited by this current sensing circuitry, not by this capacitor. But of course this only applies on startup, and then when it reaches the desired voltage at the output, the feedback starts limiting the duty cycle. Basically, as the transistor in the optocoupler passes a current through this, there is a voltage drop on this resistor, this side is positive and this negative, so it basically biases this transistor base, so it actually turns on by a lower voltage drop on this resistor. So basically this transistor turns on earlier, and so this one turns off earlier. The more current through this LED, the more current goes through this transistor, and the more it biases the base, so this transistor turns on at a lower voltage drop at this resistor. Basically the primary current and also the current through this resistor and also its voltage drop looks like this. And the transistor switches like this. This is on, off, on, off. And when it runs at maximum duty cycle, it probably turns off when this resistor drops about half a volt. But the feedback through the optocoupler can actually make it turn off earlier. It shifts the threshold basically, and then it looks like this. And also the transistor turns on for a shorter time. For example, if the optocoupler passes 2 milliamps through this 150 ohm resistor, it drops 0.3 volts, and the voltage is in this polarity on it, and so you're adding 0.3 volts to the voltage drop of this current sensing resistor, and because the transistor turns on at about 0.5 volts on its base, and you have 0.3 volts bias here on this resistor, it's enough for this resistor to drop just 0.2 volts. And then this transistor turns on and this one is turned off. So this is how the pulse width modulation is done with no chip. And so this all makes sense to me so far, but there is this other circuitry with this resistor and zener, this capacitor, another capacitor and resistor, and this double auxiliary. I really don't understand why the double auxiliary is necessary. I think one would be enough to charge this capacitor for the optocoupler, but they have a double auxiliary and it's basically rectified in both half cycles, probably both forward and flyback half cycle. I'm really not sure if this is necessary, because of course one of the windings has a lot of functions here, but the other one is only for this diode. Maybe it would be enough to rectify it from this side and completely omit this winding. But now of course the question is, what are the directions of those windings? Well, I can do some oscilloscope measurements, but let's try to think about it first. when this transistor is on, it has to be kept on by quite a large current into its base, because those big bipolar transistors are meant to switch a large current and they have generally a low current gain. So to keep them fully on, the base of it needs a large current into it. And those resistors are quite a high resistance, so they pass a low current. They are just for the startup. They are not going to keep the transistor fully on. So the only path for a high current is basically this resistor. This is the only place where a high current can come from. And of course, to pass a current into the base, you have to have a positive voltage somewhere here. So when the transistor is on, this end of this winding has to be positive. And when the transistor is on, this primary is positive here, negative here, so the dot is negative. And so I would draw a dot here. So when the transistor is on, it's negative here, positive here, and it wouldn't make any sense for those diodes to be on both at the same time, so I would guess this winding is like this. Those diodes are probably passing a current alternately, and when this transistor is on, this winding supplies a positive voltage and passes a large current into the base. It simply can't be the other way, because if this side was negative when the transistor is on, there is nothing to keep the transistor on, basically. And it also wouldn't oscillate because it would be a negative feedback, not a positive feedback. And then there is this weird circuitry with two capacitors and a resistor, which is actually a negative feedback, kind of, because when the transistor turns on, there is a positive voltage suddenly, and it will pass a current into the small transistor, and this one will try to keep this one off. So it's a negative feedback. It will kind of slow down the process of turning on for this transistor, because initially it will actually try to turn it off through the small transistor, but then those capacitors charge, and so it no longer has an effect. So I'm not really sure what it does, but it's probably to slow down the turn-on process, maybe to reduce interference, or I don't know. Or maybe to reduce the reverse recovery problems for this diode and this diode. Because if the transistor is turning on slower, then the peak reverse recovery current in those diodes will be smaller. Because of course diodes don't turn off immediately. They need some time to turn off when going from forward to reverse. So basically when the current in the diode switches from forward to reverse, the diode briefly passes a current in reverse before it manages to turn off. And so this is the possible explanation of those capacitors and this resistor, and now the question is, what did this Zener and this resistor do? It looks like some overvoltage protection, which kind of shuts it down or reduces the duty cycle in some kind of overvoltage. But is it the overvoltage at the input or overvoltage at the output? Which is basically an open loop protection. But given that it senses the voltage on this winding when it's in forward, it kind of senses the input voltage, because the forward voltage on the windings basically depends on the input voltage. So it looks like this is kind of limiting it when there is minus overvoltage. Some power supplies also have so-called open loop protection. Let me explain it. It's basically a protection against the feedback breaking. Because if something breaks in the feedback from the secondary, it can't sense the voltage on the secondary side, and the voltage would go up and up and up until something fails or until it destroys the load. So some power supplies have a second way of sensing the voltage roughly. If the feedback with the optocoupler breaks, they have a voltage sensing on the auxiliary winding in the flyback direction, so they can roughly sense the voltage at the output. Because of course the voltages are roughly proportional on the windings. If the voltage on the auxiliary winding in the flyback direction is too high, it can tell that the output voltage is probably also too high. And this is called an open loop protection. If the voltage of the auxiliary winding in the flyback direction is too high, it will limit the duty cycle. And this emergency limiting is usually set a bit above the normal voltage limiting. So, for example, when the feedback fails here, it will go to about, let's say, 5.5 or 6 volts, and then the open loop protection will start limiting the voltage. Or in case of power supplies with a chip, it may completely shut down when it detects open loop. But in this case, it doesn't seem to be open loop protection. It senses the voltage on the auxiliary winding in the forward direction. When this transistor is on, the rectified mains voltage is connected to the primary and this diode is in reverse. And basically the positive voltage from here is proportional to the input voltage, not to the output voltage. It's basically the forward voltage on it. But on the other hand, the flyback voltage is proportional to the output voltage in a flyback power supply. This is actually quite a black magic, and sometimes it's easier to understand a schematic with a chip than a schematic with just discrete transistors, actually. And now let's try to connect my oscilloscope to it to see what black magic is happening in it. I will try to measure the waveforms on the secondary winding, on the auxiliary winding, and maybe also on this sensing resistor. And by measuring the waveform on those windings, I can also tell their directions to confirm this. So here's the secondary winding on the oscilloscope, and when it's not loaded, it's a mess as usual. It's a short pulse of the transistor, then the diode is conducting here, and then some sine wave ringing, and then it repeats. Now let's try to load it. 3.2 amps load using this lamp. It looks much nicer now. You can see it switches at about 60 kHz and it's a nice waveform, almost a square wave. And here the transistor is on and the diode is in reverse. And here the transistor is off and the diode on the secondary side is conducting. And of course the voltage scale of the oscilloscope is probably wrong. This middle line is 0 and the positive plateau here is about 5 volts plus the voltage drop of the diode. So it's about 5.5 volts here. And the negative peak seems to be several times higher. It could be, let's say, 15 volts, maybe 18 volts. As you can see, the peak voltage is different in each polarity and also the pulse length is different in each polarity. The transistor is not switching exactly 50%. And in flybacks in general, the mains ones, the duty cycle tends to be less than 50%. So the positive voltage is actually lower than the negative, and also this makes the voltage overshoot on the primary lower. And thus the voltage rating of the switching transistor can be lower. Now let's try to load it more with 2 lamps at 6 amps. And you can see that the frequency is now lower, so it's not a constant frequency. Of course, with no chip, it's very hard to keep a constant frequency. And now let's try to turn the potentiometer in it, and now turning the voltage up or down, up, down. And you can see that when I turn the voltage up, the transistor is on for longer. Up, down, up, down. For a higher voltage, the duty cycle of the transistor is higher. But the voltage here, the voltage level, is not changing here with the output voltage. Just the pulse length is changing. But on the other hand, in this polarity, the peak voltage is changing. Of course, the flyback voltage on the secondary is changing with the output voltage. And now let's try to measure the waveform on the auxiliary winding. And of course this is dodgy because it's on the primary side, and the ground of the oscilloscope goes here and the probe goes here. And of course I can only do this with an oscilloscope which is not grounded. My one is battery operated, but this actually makes the oscilloscope live at minus voltage, including the metal connector. And what it shows, it looks very similar to the secondary, except there is a little bit more ringing because the auxiliary winding is not much loaded. And the amplitude is similar, just a little bit smaller, so this auxiliary winding has a little bit less turns than the secondary. And the waveform seems to have the same polarity as the secondary. So this proves that those dots are right. Now let's check this side of it. Let's see the other side of the auxiliary. And the waveform is in the other polarity. So the other side of the auxiliary goes in the other direction, apparently. So this dot is also right. This end of the auxiliary is positive when the transistor is on. The transistor is on from here to here. Now let's try to measure the waveform on the current sensing resistor to basically see the current waveform. And that's the current waveform. And here the transistor turns on and the current goes up gradually as I expected, but for some reason here it no longer goes up, and then the transistor turns off and the current disappears. And when the transistor turns on, there is some short current spike. And this is probably maybe because of the capacitance of the primary winding, or also maybe the reverse recovery current of the diode in the snubber network and the secondary diode. And here's the base voltage of the main transistor, which is of course positive when it's on and negative when it's off. Well, here's the actual base voltage, base to emitter voltage, not base to common 0 volt rail. So the voltage on the current sensing resistor is no longer added to it. And you can see that the voltage drop of the base to emitter junction is more or less constant. Now let's try to see the high frequency ripple of the output voltage, which should be higher before the inductor and lower after the inductor. And of course let's measure it at a full load, or nearly full, about 9.8 amps. And here's the voltage ripple before the inductor. And the voltage ripple after the inductor, the same scale. The ripple is significantly lower after the inductor. So having an inductor and a second capacitor makes a big difference. And now let's try to use the NTC thermistor as a current sensing shunt to see the input current waveform, which is definitely going to be far from a sine wave because it has no power factor correction. And here's the input current waveform at 50 Hz. And of course it's a rectifier with a big capacitor and no power factor correction, so it's definitely not a sine wave. The bridge rectifier basically passes a current only at the top of the sine wave, at the peak of the half cycles. And let's try to zoom one peak. So this is the current in each half cycle. And I quickly measured the efficiency of it, which is the output power divided by the input power. And the output power is the output voltage times the output current, and the efficiency was 73.4%. It's not a ground-breaking efficiency, but you have to remember that it's a bipolar transistor, and also lower voltage power supplies are generally less efficient because the voltage drop of the output diode is more significant. And the power consumption with no load is about 3.1 watt, 3 watts, and the 10 times more sensitive socket says about 3 watts too. But of course it's a power supply with a bipolar transistor and no control chip. The ones with a MOSFET and control chip are generally more efficient and draw less power with no load. So this is Diagonal Wild, and see you in my next videos, and thanks to all of my patrons on Patreon. I really appreciate your support. And my patrons get early videos 2 days earlier. And I plan to fix and explain more switching power supplies in my future videos.